And aren't you okay with being recorded?
Yeah, I'm fine.
You starting at 5 past? I need to make a quick phone call, so I'll come back.
Do you know how to turn the fence on?
Normally it's these.
Oh,
Are you Christine? Yeah. I'm Francis. Nice to meet you.
Oh, nice to meet you. Yeah.
Well, I'm doing that at work.
mate, you're the best friend.
Yeah, I want to come to this. Yeah, yes. Thank you. The school is a little bit empty because we're between terms and.
But I'll try.
Oh, when can I have 50,000 students come back?
Set up thing with you. But I mean, like, when you're on the next step. Okay, so you're not planning to get
Time. Yeah, it's okay.
Recess to enter the.
Where were you before? Okay, so not from Australia. They're horrible. They give jobs like.
Yeah. If you get to know people. Yeah.
This is very good. Seeing those all time favorites. After the COVID, yeah. Where would you been to you?
We do the changeover, we'll have to make sure the camera tracks you and not me. Yeah.
Just all advertised, yeah. That's good to say. Never cross the ring.
All right. Good afternoon, everyone. Thanks for coming. It's nice to see so many of you here. I think this is the most packed seminar we've had in probably years. So today we have Professor Art Owen from Stanford University here. Art needs essentially no introduction, but he's made several significant contributions to Monte Carlo and quasi-Monte Carlo theory and empirical likelihoods. So we're very happy to have him give us a talk today on complexity across random effects. Please, Art, go ahead. I will just make sure that we can get the camera to track you. It's tracking me. I find you.
I'll do this. So if you lose this track of you, say, honey, does it turn off? That's it. Okay, well.
Maybe if you now walk back and.
All right, well, it's AI and work. Well, thanks, everybody. Thanks, Sahani, for the introduction. And thanks, everyone, for making room in your schedule. Like, you could be between, you could be at the beach between investors and here. This is some joint work did with my colleague, Trevor Hasty, and the student that we jointly advised. Warren was amazing. He was able to understand everything I said and did and everything Trevor said. The reason this is possible is because Warren did. So first of all, try to convince you why I care about cross effects, especially cross random effects. So you might have to study plant varieties and the environments they grow in, or customers and products. Hospitals could send anybody to, the hospital might send you to this dialysis center or that dialysis. And when you look at what happened to the kidney patients, they come from this hospital and that dialysis center, or just a different combination. And these are many to many mappings that I'm going to do. There's a famous data set from Netflix where there were 100 million movie ratings. That's kind of a mental model for this sort of problem. And we were able to get 5 million clothing ratings from a local company called Fitness. Now, when you have this cross random effect situation, we know exactly what to do statistically. We should use generalized least squares, or we should use some sort of Bayesian approach. The very first thing you take off the shelf to use will have a cost that's like infinitely has power, or even worse. So now in a world of big data to the chart we have suddenly quite uncomfortable. So this 3 halves power was established in some work with Caitlin Gap, your PhD with us some time ago.
Sorry, can you talk a little? People
Okay.
like it.
Okay, so okay, so I will speak a little bit louder. Okay, so what I'll talk about today are recent contributions with Hasty and Ghosh. With generalized least squares and a backfitting strategy, we can do this in order n computation per iteration. Then the heavy lifting was make sure that you don't need a number of iterations at those. And so we were able to have order n work per iteration and order 1 iterations. That was actually the hard part, I will skip over the details of the hard part. But for me, the hard and interesting part was making sure that it's order 1 iterations. And we've since extended it to logistic regression. I might not have time to talk to you about logistic regression today. I was just reminded some years ago when I spoke, Robert Cohen had this idea to take people out for alcohol before they talked. And that's in honor of that, I might not get through all the slides, even though I didn't have the alcohol. If I'm pushed for time, then I'll come to just regression. Okay, so when you teach an introductory statistics class, one of the things you tell people about are categorical variables. And so a categorical variable might be somebody got the cancer treatment, somebody got the placebo. Or it might be there's 3 different kinds of iris flower in the Gascade Peninsula. Or maybe 50 states in the US. That's a pretty typical categorical variable. That's not the kind of categorical variable that we're talking about. We're talking about, you could call them factors. So suppose you're a store and you have stock keeping unit numbers, and one of the things on your shelf is a dust filter for a Hoover Max Extract Pressure Pro Model 60. If that's what the customer wants, there's nothing else different from that they would want. The Model 50 wouldn't do it. So with this kind of a categorical variable, there could be millions of levels. Think of everything that Amazon sells. Each of those things could be one level of your categorical variable. So that's different than 3 kinds of iris flower. Or a query string. If you go to a search engine and type something in, what you just typed is a level of a categorical variable as far as they're concerned. So somebody might have typed something fairly popular, like you type in Australian Open. Somebody else, I might be there typing in heteroscedasticity. And some of these query strings are much more frequently typed in than others. And every day Google will get query strings that they have never seen before. So there's a Pareto law or a heavy tail distribution to some of these categorical variables. Again, different from 3 kinds of iris flower. Then there are things like a URL, an IP address, a customer ID. These things have a way of appearing, becoming more popular, and then disappearing. So the companies call this churn. So some level of your categorical variable might appear and then later disappear. Anyway, you might want to treat those as factors in a cross random effects model. I'm not going to insist that you must do that or that it's the only way to do that. But our feeling was if you wanted to do that, it should be possible. Here is an example. In the Internet Movie Database, it can tell you which actor was in what movie. And so we could sort all the actors from the ones in the least amount of movies to the ones that were in the most movies. And we could sort all the movies from those with the least actors in them to the most actors. And then every time an actor was in a movie, we could put a smidgen of ink on that square. And then what you're looking at is actually a copula. And then you can see some non-uniform pattern. Wow, it's really dark up here. Actors that were only in a few movies are very likely to be in movies that had a lot of actors. Okay, so that kind of makes sense. If you're one and only movie like you were in, like you up here. And then actually it's kind of sparse down here, a little dark on that side. So you can look at these kind of patterns, and this is what might be underlying the data that we're trying to move. So one of the simplest models that you could have for cross random effects. I'm sorry. Mouse has jumped to different screens. How do I get him back on here?
It's just through that corner.
Oh, so it's off the lower
Yeah.
right. Okay.
Yeah.
It's the okay. So the topology is very. Okay. So suppose you have person I buying object J, and that would be Yij would be how much they like it. And then what you could do is a linear regression model, but Xij is some kind of features. And data. And then the random effect comes in. Well, let's suppose that some subjects just like everything that you offer. Some don't like anything that you offer. And that could be a random effect. And some products are just better than you would predict. And if B is positive, people just like them more, or if it's negative, they just like them less. You can have a random effect up or down for the person, up or down for the product, and then of course goes on top. That would be a very simple random effect model. And then these A's are random, B are random, and this epsilon is random. And this is one of the first things students see where, wow, there's more noise variables than data or than responses, which is their combination. Okay, so this is a pretty simple model. If you were comparing it to a neural network and counting layers, one, okay, so one layer. I think for factor analysis and genres and interactions, communities, there's none of them there. This model could have been worked on by Henderson in the 1950s before integrated circuits became invented. In fact, Henderson did talk about models like this. So this is a model that's like 7 years old, and you can't do it on the computer. Just evaluate the Gaussian likelihood one time, it will cost you endless 3 hours of work to do that. So what's happening with computers now, the data sets are going faster than the compute power. And so it's an arms race. When the data wins, then the compute loses. And if it's going like endless 3 has, well, you can't keep up with that. Okay, so when we discovered that, everybody said, well, you should just use a Bayesian solution. And Caitlin Yao took a deep look at that, and a Gibbs sampler will take about square root of n iterations to get to stationarity. Every iteration costs you about order n. So you're again looking at n that 3 has work, whether it's regressions or both. That's the problem we wanted to. Why is there a field of statistics? It's so you can tell people about numbers that they don't have using the numbers that they do have. It's all about generalizing. And you can generalize if things are repeatable, reproducible, and replicable. So you want replication. In the world of IID data, it's very easy to have something replicated or to study it. Hierarchical data, well, that's just like IID clusters. Get an independent cluster and then another one. The data come to you in clumps with dependence in them, but between clumps, it's independence. Second easiest setting. Cross-random effects are a big tangle. Suppose I hold out half of the customers. They're correlated with the customers I didn't hold out because of the products that they buy in common. And if I held out 10% of the products, that data is correlated with the data I held in because of the shared customers. So instead of having repeats embedded in the data, it's one big tangle. It's like something complicated. So that's what makes cost effects harder than nested effects. Here's some notation of capital R rows and capital C columns in the data. The row could be a customer and the column could be a product. You have this variable Zij, and there's just a 1 if we got that data, there's a 0 if we didn't get the data. And then in I dot, that's how much data we have on customer I. So we just sum the Z's over products J. And n dot J, that's how much data we have on product J. Then we sum over the customers. And then the total amount of data we have is the sum of, you can sum it this way or sum it that way, it's the same. The motivating settings are very sparse. So the number of rows we have is much larger than 1, and so is the column, number of columns. However, the number of rows or columns is much less than the total amount of data. So in particular, no one row has half of all the data. The amount of data that we have is much less than the number of rows times columns. They're very sparse. In the Netflix data, meaning 1% of the movies are rated by a person. So if that 100 million was only 1% of all the possible ratings. Most people do not rate all the movies. If you had a balanced experimental design and you mapped out the Zi and J's, they might look like a grid. Everybody bought every product, or everybody rated every product. In a hierarchical model, the row variable is nested in the column. So if you're in rows 1, 2, or 3, that means 1, column 2 has some observations that don't the other column. All four has some observations that don't appear that way. This is a hierarchical model, and you can transpose it in this hierarchy. You're in a world where you never saw the same row column twice, you would have IID data. This is the kind of world we're looking at. I showed you the IMD. This is arbitrary mishmash. Which person rated what thing? The missing list pattern is informative, or could be. People rate movies they like. People rate restaurants they don't like. And there's a sort of bias. And they rate the ones they like too. That's, we are going to ignore that because the problem was unsolved even without that. And I don't think there's a lot of great solutions out there anyway for him to perform this. So we sized that. Okay, so the right thing to do is generalize least squares. All of that stuff. And the simple thing to do is ordinary least squares. So ordinary least squares have this mantra x transpose x inverse x transpose y. And then what's the curly x? Well, it's all of the predictors from all n rows. And curly y is all of the responses. And you have to be careful that they're in a compatible order. And then this v is an n by n covariance matrix. So for Netflix, it's 100 million by 100 million covariance. We're going to assume that the dimension of x and beta is fixed. It's not growing asymptotic. It's like 30. And these are going into millions. Okay, so this would be pretty easy to do. This is a thing that takes advantage of 3 halves. Okay, so what's the problem with ordinary squares? Well, the first problem is it's inefficient. You're going to get more variance than you could otherwise get. The variance is too big. Well, if the variance is too big, you get low. You get more type 2 errors. This thing you should find. The other problem with OLS, and I think is more serious big data, is that it's naive. Ordinary squares, it's ignoring all those correlations. So it's way more confident than it should be. The variance estimate that it feeds you is way smaller than what it should have been. So you're going to have false discoveries. What's interesting about this statistician is, wow, we have a way to get more type 1 errors and more type 2 errors at the same time. You just switch from generalized least squares to ordinary least squares, and you can increase both kinds of errors that usually we think of as a trade-off. At least it's consistent. We will use that. Okay, so why is it hard? I want to show you why it's hard. And here's a toy example with 8 observations. We have 3 customers, 1, 2, 3, and we have 4 products, 1, 2, 3, and 4. And here's the Z matrix. Customer 1 did rate product 1. So they have a 1 where the rating happened and a dot where the rating was missing. And then let's just label those observations 1 through 8. So here, customer 3, product 2, that's observation 7, was customer 3 saying something about product. And now let's look at the correlations. If it's the same customer, then there's a correlation. So here's a block matrix of correlations in the customer random effect A. And so these two data points came from the same customer. And the second customer gave those 3 data points. And so we have this correlation structure in random effect for customers. And here's the random effect for the product. And the first product was rated by customer 1 and 6. So you get a block of 1s in that correlation matrix. And again, it's also block diagonal, but the rows and columns are in a different order. You have to order the data differently in order to make it block diagonal. And if you put them all in the row order, then the covariance matrix is sigma A squared for customers times blocks of 1s. So sigma B squared for products times permuted blocks of 1s. Plus sigma E squared times an identity matrix. You can't really invert that matrix very easily. These matrices are not simultaneously diagonalized. There's 3 of them in there. Herman Morris and Woodbury will not help you. If you only have one of these effects, you could use Sherman laws and library, but with two of them you can't. In the linear mixed effect model, the naive algebra would NQ work because it's n observations. The actual algebra is not NQ. That base shows another is R plus C cubed. Number of rows plus number of columns. Okay, so here is sort of the kindergarten complexity level. If R times C is more than n, one of them has to be bigger than the square root of n. Where my math undergraduate theory training come in beautifully for me. One of them has to be more than the square root of n, and so when you cube it, it has to be more than n. So that's the intrinsic complexity problem that you get stuck with in cross-parameter effects. And so cost models, the cost is superlinear, nested models, everything is block-wise and it's linear. And we clocked Doug Bates. The best code I believe is by Doug Bates, and it clocks in at n of 3 halves, 2000 like at one time, do one iteration, n of 3 halves. What about Markov chain Monte Carlo? Well, I mentioned and Caitlin Gao did a lot of work on MCMC. And every time that we found MCMC failed, people would explain to us we had chosen the wrong MCMC. And so we only got to the 7 of them. And then the 8th one that somebody else did worked. So, however, it's pretty hard. It's not obvious. So here are the various things, reparameterizing. A lot of people know that that helps. It doesn't help in this. And yeah, so there's lots of things that you could try with MCMC and it wouldn't really work. And then Bates et al. Actually they took Bayes out of LME4, not because Bayes was unreliable, but because computing it was. So what do people do? Economists use OLS, but then they're clever not to use a Huber-White covariance. So they're clever not to be naive about the covariance, but they'll be inefficient because they're using OLS. Gao had a method of moments method that was efficient if one of the random effects dominated, otherwise inefficient, but not naive. The right way to do Bayes is a collapse if sampler. I'll say more about that later. There's Papaspiliopoulos, Logers, and Sinella. And what they do is they analytically integrate out the intercept. It's a huge improvement. I don't quite like their assumptions. They assume that every person bought the same number of products. Every product was bought by the same number of people. We felt that that was too strong of an assumption. They didn't think so. Yes.
Yeah, presumably MCMC doesn't work with the correlations when you do stuff. We've often found that just as a slight, it's a huge improvement on MCMC.
Right. Okay, well, that I'll look into that. Because so this is sequential Monte Carlo?
Yeah.
Okay, so then the trick is always adapting it to the specific thing. So
we found that in places where deep sampling doesn't work at all, like Instagram. Once we put it through the SMC, we could use GIF sampling and only PMH work for MCMC. That is, integrate stuff out in quotes. We found that in those sort of models, maybe on these ones, but in those sort of models, SMC worked well just on the GIFs. You didn't.
So keep that in mind because I'm talking to another student who's jumped into an MCMC, and the first thing that he finds is it doesn't mix. It's an environmental problem, so we're always on the lookout. In the PRZ paper, they also say that the mixing time is order 1, but if you read the fine print, it's order 1 times an unknown that we don't know. If it's order 1 times an unknown. The unknown. Well, I'll show you what that unknown is later. Okay, so So my colleague Trevor Hasty is a big fan of something called backfitting. And here is how backfitting works for cross-parameter effects. And this fundamental paper by John Robinson. If you're going to do the generalized least squares, the estimates you would get by minimizing this quadratic. Okay, what's in our quadratic? Y minus x beta, so that's the residual. ZA times A, that's something that puts A sub I for every data point that was customer I. And ZB times A B is something that puts B sub J for every product customer pair that involves product. This ZA is got N rows and it's got R columns, one column for a customer, this is one column for product. And then it has these ridge penalties on top of that quadratic. So if you can solve this set of equations, then you solve generalized least squares. And these are variance ratios. Okay, so then the basic idea in backfitting is we'll update A, then update B, then beta, then back to A, B, and beta. Just keep iterating, solving for one unknown at a time. And it's also known as Gauss-Seidel or block limit. If you only had the one random effect, then it would be used to minimizing this quadratic with a penalty on the. And what would you do? Well, you differentiate this with respect to beta, differentiate with respect to A, set the derivatives to 0, gather everything up, and what you would get would be this expression. This is Z times A hat. So this is what you're going to predict for anything purchased by customer I coming out of this matrix. And what is it? It's stuff times the residual. And then what is all this stuff? So Trevor looks at that and says, well, it's a smoother matrix. And if you look at it closely, what it's actually doing is taking an average in rows and then shrinking that average towards 0. Take all the data that came from the same row, take its average of these residuals, and then we'll shrink it towards 0 in a ridge prediction fashion. Okay, so beta hat then has this expression in terms of a smoother matrix. Generalized least squares, where the thing in the middle got replaced by identity minus the smoothing matrix. If you have two effects, then you can do a row smoother and a column smoother and alternate the smoothing. And there's a proof that it converges to a two-factor smoother. And that's what we'll use to update beta. And there's a lot of details. This costs you order n to do one iteration. So now the fight is make sure that the number of iterations is not growing. Now, you can prove that when you're done with backfitting, the estimates of the row effects are going to add up to 0. If they didn't, you could tweak the intercept of the model and make it so. And the column effects will also add up to 0. And so instead of making the algorithm discover that fact, you can bake it in so that in every iteration, this exactly happens. So, okay, so that's was the key step to making the backfitting work properly. Now I'm going to switch over and tell you about the data set that we illustrate. So Stitch Fix is one of these California.coms. What they would do is they mail you a box, and you open up the box, and there's 5 things in it that they think you want to wear. And you keep the ones you like, and you mail back to this. And then there's a combination of a computer algorithm and a human curator deciding what to send you. And so they sent us some data on people who get a product, they rate it on a 10-point scale. And the data that we got, there was a customer, and an item, and didn't get the price, but you can imagine they would definitely have the price. And there's like, what's the size of it? They care a lot. Like, does that size actually fit you? What's the material made of? They would have all kinds of data on you, and we will look at just this plain linear model. And so we have this on a 10-point scale, and Brad Klingberg got the data for us. It's extremely hard to get data from a company. We're very fortunate that one of our former students was willing to help us do this. So in that data, there's 5 million ratings, 700,000 or so clients, and about 6,000 items. And rating on 10-point scale. One of the predictors was an old algorithm predicting, does this item make sense for that person? Also, is the item edgy? I don't know exactly, I'm not a fashionista, so I can't tell you what edgy means, even in California, like it might be something different in Australia. And an item could not just be edgy, it could also be boho. That's short for bohemian. And not only could the item be edgy, the client could be edgy. And the client could be both. And I think you can do both. I haven't tried that. I think you can. And then the material type, was it leather, fur, wool, fabric? That was the variables in our model. And we just looked at one regression, just one. In a company, this would be the first one you do, then you'd reject it for some reason, and you'd probably look at 10 or 20 more regression models. But we just want to look at one and see what happens. We're going to explore how bad ordinary squares is. And then you need our algorithm, you need these variance components. And Caitlin Gao, in her thesis and in a paper, she has a method of moments ways using U statistics to actually estimate those all in our order n budget. So here's our model. On a 10-point scale, how much did person R like thing J? It has an intercept regression on prior match variable. Makes a difference if the client's edgy, or the item, or the boho. We even have something if the client is edgy and the item is edgy. And that turned out to help. There's a synergy between, if the item and the client are both edgy, they're more likely to like it. Didn't work for boho. And a categorical variable for material. That was the analysis. And here we look at how inefficient ordinary squares is. So there were 30 parameters in that model. And we can look at what's the variance of ordinary squares, our best estimate of that. What's the variance of generalizing squares? And it ranged between about 1 and about 50. And for sake of argument, suppose the ratio was 5. And that's kind of the middle of that histogram for all 30 variables. If the ratio is 5, you're getting 5 times variance that you should have got. Or then you're getting 20% of the information you should have. So it's like you're ignoring 80% of your big data set when the factor is 5. When the factor is 50, of course, you're ignoring almost all of your data. And so ordinary squares is pretty inefficient on that data. What about naivete? So we have some idea of, well, what does ordinary squares think the variance is? And then what do we think the variance really is, using generalized least squares understanding? And that ratio was between about 2 and about 350. But this is actually the scarier plot for me. Suppose you're at 100. So you're naive by a factor of 100. The variance is 100 times what you think. That means your confidence interval is 10 times as wide, 10 times narrower than it should be. That means when you're thinking you have 95% confidence, you have about 15.5% confidence. At least you get that extra half. So I feel like with a big data set, you don't have to be perfectly efficient. But being excruciatingly naive, I think that's pretty bad. So you'd be finding all this stuff in the big data that's just a hallucination or mirage. That's why we wanted to do generalized least squares on data like that. Okay, so what about convergence? So when you're backfitting, you update the A variable, you update the B, you update beta. If it's not A and B both, then beta is trivial computation because it's a 30 by 30 matrix in this case. So that's not to worry about. The worry is there's 700,000 A's and 16,000